Welcome to my lecture on optical networks. In this lecture, we talk about the optical networks in general, and also we talk about the WDM networks in optical communication system, and also specifically we talk about a fiber nonlinearity effect called four-wave mixing in WDM networks. The outline of my lecture is given as follows. We start with a brief overview of the optical networks. Then we talk about the WDM transmission technology, its basic block diagram. And then we talk about the nonlinearity effect called the four-wave mixing in WDM system. Specifically, we talk about the FWM efficiency, and we conduct a quiz, and also we solve a tutorial problem on the four-wave mixing effect. And finally, we conclude with the lecture summary. So in general, the optical networks are very much important nowadays. So we are actually using optical network in our daily life for transmitting and receiving data. For example, if you want to access a data or information which is saved on a remote server, you need optical networks to convey that information from long distance. So by definition, optical network is a telecommunication network with transmission link that are optical fibers used to transmit huge amount of data. So optical fibers are essentially thin glass cylinders which guide the optical signals by total internal reflection. So optical fibers are one of the important component in the optical networks. So in high performance optical network includes several combinations of electrical and optical devices, and essentially an optical network connects computers, various devices across the globe, or intercontinental connections are through the optical cables. So optical networks are used to connect or interconnect people in general, and also the devices that can store or generate data. So why do we need optical networks? So this is one of the important question we need to discuss. So day to day, the demand for bandwidth is increasing because a tremendous growth of connected users are there. We use mobile phones and we transmit and receive data, and we send messages, video messages. So for all these huge bandwidth applications, we need a high capacity channel to carry your data. So optical fibers are used for that. So optical networks are very important. And other applications, bandwidth intensive applications like even browsing in a World Wide Web, other large bandwidth applications like cloud computing and virtual reality, video conferencing, even downloading a movie, we need huge amount of data has to be transmitted through the optical fiber channel. So in general, the optical network system consists of a transmitter and the receiver. So at the transmitter side, we essentially convert our information electrical domain to the optical signal, then transmitted over the fiber. At the receiver side, we do the opposite conversion, that is optical to electrical. Then we do the demodulation and detection of our information or data, which is transmitted through the optical fiber. So to utilize the huge available bandwidth of optical fiber, we use a technology called wavelength division multiplexing. So WDM is a technology used to increase the transmission capacity in optical fibers. So what is WDM? Basically, by definition, WDM is a fiber optic transmission technique that enables the use of multiple light wavelengths or multiple colors to transmit information over long distances. We modulate optical light or each wavelength with different user data and multiplex together and transmit over the optical fiber. So here, this block diagram shows the WDM system for a point-to-point optical network system. So the blocks inside this rectangular box shows the transmitter side. Here I have shown the dual polarization system. That means we use both X and Y polarization to transmit information. So in each polarization, we have several wavelengths, lambda 1, lambda 2, up to lambda n. We modulate each wavelength with different information data, and we multiplex together, and the WDM signal from X and Y polarization are combined using a polarization beam combiner and transmitted over the optical fiber. So the optical fiber link here is a point-to-point optical link. It consists of a recirculating loop of optical fiber. In general, a dynamic optical network, other topologies are available. Like in such cases, there are additional components like auto-drop multiplexers are there. I mean, for for the networking in a different topology. So at the receiver side, we do the opposite operation. We demultiplex information from different wavelengths and demodulate and detect our transmitted information. So this is a very general basic block diagram of the WDM system. And there are two different types of WDM. One is the coarse WDM and another is the dense WDM. That depends on the spacing between the WDM channels. The figure on the right bottom corner shows an example of a DWDM system where 4 different frequencies or wavelengths are used to transmit information. And the modulation format used is a dual polarization or polarization multiplexed QPSK. By having these 4 wavelengths, each having 100 gigabits per second, in total, we can transmit 400 gigabits per second data over the optical fiber. So this is how we can increase the capacity of optical fiber network. Even though WDM has several advantages, the disadvantages are also there. That means the four-way mixing is one of the predominant kernel linearity effect. So WDM systems are susceptible to the four-way mixing problem. So here we will talk a little more about the four-way mixing. So what is four-way mixing? Four-way mixing is an intermodulation phenomenon in optical fiber where the 3 different wavelengths interact nonlinearly and produce a 4th new wavelength. So this is clear in this right figure. You can see that the WDM channels, the JSON channels interact nonlinearly and produce nonlinear beating components. So they are called a four-way mixing. So this causes crosstalk between the JSON channels in WDM. Also, it causes the imbalance of channel powers. The bottom figure clearly shows how the 3 frequencies F1, F2, and F3 interact non-linearly based on a phase matching condition F1 plus F2 minus F3. At that frequency, it will generate a 4th wave. That is the 4-wave mixing problem in optical networks. So one way to suppress this is avoiding an equidistant channel spacing. So if you can have a variable channel spacing between the WDM channels, we can reduce the effect of FWM up to some level, but still we cannot completely avoid the effect of four-wave mixing. So there are 2 types of four-wave mixing problems. So essentially, as we discussed in the previous slide, the four-wave mixing is a nonlinearity issue. It generates because of the nonlinear beating between 3 frequencies, let's say omega j, omega k, and omega l. According to the phase matching condition given by this equation, omega j plus omega k minus omega l is equal to omega n. That means the triplet pulses. We say we have 3 frequencies and 3 pulses and 3 frequencies interact together, or those triplets interact together to generate a 4th pulse in the 4th frequency. So J, K, L, and N are the indices of the pulses in the each wavelength channel. So there are 2 types of four-way mixing. One is a non-degenerate four-way mixing, and second one is the degenerate four-way mixing. This depends on the the index values which are taking part in the generation of four-way mixing. Here you can see the different combinations of J, K, L, and it will generate non-degenerate and degenerate. So from this table, it is clear that in the case of distinct indices J, K, and L, we get non-degenerate. But in the case of if J is equal to K and it nonlinearly beat with the, the signal at I index generate a degenerate kind of four-way mixing. So the figures on the right bottom corner clearly explains how this non-degenerate and degenerate four-way mixing components are generated because of the nonlinear beating between the 3 wavelengths or frequencies. So here we talk about how we can compute the four-way mixing efficiency in a WDM system. So the impact of four-way mixing in WDM system is basically quantitatively described based on the efficiency of four-way mixing components generated in the optical fiber. So this four-way mixing efficiency depends on several factors like frequency separation between the channels, chromatic dispersion parameter of the fiber, fiber length, and the attenuation parameter alpha. So The equations given in this box are basically used to calculate the four-way mixing efficiency. So eta jkln is equal to alpha square plus 4 exponential minus alpha L sine square delta beta jkln into L divided by 2 divided by L effective square divided by alpha square plus delta beta jkl whole square. So this expression basically calculates the efficiency of four-way mixing components in the WDM system. Here the L effective is given by this expression, and delta beta jkln is actually the propagation constant we can compute using this equation number 3. So before going to the tutorial problem on this calculating the four-way mixing efficiency, we have a short quiz, a quick quiz. This basically gives you a strong understanding on the nonlinearity and the four-way mixing problem in WDM. So the question number 1 is, the equidistant channel spacing reduces FWM. Is it true or false? Second question is, which of the following effect causes nonlinearity in optical fiber? And the last question is, for the given frequency combinations, which one generates a new frequency at omega 4? So here are the answers. So for the first question, the equidistant channel spacing reduces FWM. The answer is false. That we already discussed in the previous slide. Which of the following effect causes nonlinearity in optical fiber? Kerr effect. And the last question, for the given frequency combinations, which one generates a new frequency at omega 4? So answer is option 4. That is omega 4 is equal to omega 1 plus omega 2 minus omega 3. That is the phase matching condition we have discussed in the previous slide. So next we try to solve a tutorial problem on the four-way mixing efficiency. So this problem, by solving this problem, you will get a more strong understanding on the four-way mixing efficiency in a WDM system. So here the problem is like this. We have a WDM system consists of 3 channels centered at minus delta F, 0 and delta F, with the spacing is given as 50 gigahertz. And the fiber loss coefficient is given as alpha is equal to 0.0461 per kilometer, and the fiber length is given as L equal to 40 kilometer. So the question is, calculate the efficiency of non-degenerate FWM tone at minus 2 delta F if beta 2 is equal to minus 4 picosecond square per kilometer. So given this question and parameters, we can use this set of equations we have already seen in the previous slide. Using this equation, we can calculate the efficiency of four-way mixing. So the step 1 is we need to calculate the L effective, value of L effective, by substituting the attenuation parameter alpha in equation number 2. We can compute the L effective as 18.28 kilometer. In step 2, we try to compute the propagation constant. So here in the question is given that we asked to calculate the four-way mixing efficiency at minus 2 delta F. So the corresponding indexes are J is equal to minus 1, K is equal to 0, and L equal to 1. So that N is equal to J plus K minus L is equal to minus 2. We will get a FWM product at minus 2 delta F. So by substituting these values in equation number 3, we can compute the propagation constant as 7.89 into 10 to the power minus 4 per meter. So in step 3, we substitute all these calculated values in equation number 1 to compute the FWM efficiency. And by substituting the values and performing several simple calculations, we get the four-way mixing efficiency as 3.4 into 10 to the power minus 3. So this is an example of how we can calculate the four-way mixing efficiency in a WDM system. So here there is a practice problem. You can try to solve the practice problem using the same parameters as in problem 1, tutorial problem 1, with beta 2 is equal to 10 picosecond square per kilometer. This will give you a more strong understanding on the four-way mixing effect. So as a summary, we discussed a brief overview of the optical networks. Then we discussed the basic block diagram of the WDM system. Then we discussed the four-way mixing problem in WDM system and the FWM efficiency. And finally, we conducted a quick quiz and discussed a tutorial problem on the four-way mixing effect. Thank you so much.